In this lesson, we are going to talk about the absolute value function. First, recall that a function is a rule that takes each input x and matches it to exactly one output, which we call f at x. That's function notation. We're saying that f is the function that takes the input x to the output f at x. When we graph a function, we plot the points f at x, so it's common for people to write y equals f at x. Recall that the absolute value operation tells us the distance from 0 to a particular number on the number line. So in the same respect, the absolute value function tells us the distance from the input x to the number 0 on the number line. And we write f at x equals these vertical lines of x, which means absolute value of x. So f at 3 equals the absolute value of 3 equals 3, because the number 3 is only 3 steps from 0 on the number line. In the same respect, f at negative 3, which is the absolute value of negative 3, is also equal to 3, because the number negative 3 is also 3 steps from 0 on the number line. So if we were to graph the absolute value function, we can make a table of values. So on the last slide, we found that f at 3 was equal to 3, and f at negative 3 was also equal to 3. So these are 2 points on the graph. So for f at 3 equals 3, the x value is 3 to the, so we start at the origin, 0, 0, where those 2 dark lines cross. We move right 3 spots and up 3 spots, and we get the point 3, 3. And then we also have the point negative 3, 3, so we move left 3 spots and up 3 spots. We have the absolute value of negative 2 is equal to 2. So that would be this point here. The absolute value of negative 1 is equal to 1. The absolute value of 0 is equal to 0, so we pass through the origin, the point 0, 0. The absolute value of 1 is equal to 1. The absolute value of 2 is equal to 2, and so forth. If we connect these dots, we actually get a V shape. So the shape of my graph is a V that goes through the point 0, 0, and the points 1, 1, and the point negative 1, 1. So that is the graph of an absolute value function. We could also define the absolute value function as a piecewise function, because if we only look at the places where x is positive, so this is the right side of the x-axis, or sorry, the y-axis of x equals 0. The graph looks like the line y equals x. But on the left side of x equals 0, so when x is less than 0, so that's the left side of y-axis, the graph looks like the line y equals negative x, a line with slope negative 1. And so that is another way of writing our absolute value function, is as a piecewise function. So some characteristics of an absolute value function. We have the shape of the graph being a V. It is a V shape. it passes through the points negative 1, 1, 0, 0, and 1, 1. The graph is symmetric. The graph is symmetric over the y-axis because it's an even function, and the domain is all real numbers, and the range is all the y values greater than or equal to 0. So, recall we've talked about the transformations of functions. And so this little table here shows us all the different ways that we can move a function. So the transformation of a function means you have the same basic shape. Oops. But it has either been shifted left or right, which is here, well, it's not letting me highlight. So shifting left and right, that's these two. Shifting up and down, that's adding or subtracting on the outside of the function. We can reflect over the x-axis, so this is a vertical flip. Or we can reflect over the y-axis, which is a horizontal flip. And then we also can do vertical stretches and horizontal stretches as well. So, example, using transformations. If I look at this function, it pretty much looks like g of x equals the absolute value of x, but I see that I added 3 on the inside of the absolute value, which that is a shift left 3, because your x lies to you. And then on the outside, we are multiplying by negative 2, which that's a vertical flip because it's negative, and it's 2 times taller. It's a vertical stretch. So for our graph, we do still go through, oops, that's not true. In the original absolute value function, 0, 0, 1, 1, negative 1, 1. This is the graph of y equals the absolute value of x. But now in red, I'm going to do the transformation. We go left 3, 1, 2, 3, and then flip over the x-axis because it's a vertical flip. So we do contain the point negative 3, 0. The point 1, 1 goes left 3 to 0, 1, negative 1, 1, negative 2, 1, flip over the x-axis to negative 2, negative 1, and then it's twice as tall. So we're at the point negative 2, negative 2. And then as I move the point negative 1, 1, it goes left 3 to negative 4, 1, flip over the x-axis, then 2 times as tall. So now I'm at the point negative 4, negative 2. And I have that same basic shape. It's still a V shape, but it's been flipped over vertically, shifted left 3, and 2 times taller. So it's a little bit skinnier. Oops, I don't know why that last line disappeared. Okay. But another way we can do this is by looking at the symmetry of a graph. We know that it's supposed to be a V shape. So step 1, determine the y-intercept. And so that is where we let x equals 0. So f at 0 equals the absolute value of 3 times negative 2, which is negative 6. Then I need to solve. Negative 6 equals negative 2 times x plus 3. Divide both sides by negative 2. I have 3 equals the absolute value of x plus 3, which then tells me that x plus 3 equals positive or negative 3. So my two answers are x equals 0 or x equals negative 6. If I could get it to write that. Oops. We'll just kind of shove that in there. Negative 6. And the vertex would be right in the middle of those 2 points. So the vertex would be at x equals negative 3. And so now I just need to plot these points. Here is the point negative 3. If I plug in negative 3, I get 0. This was the point 0, negative 6. And over here, I have the point negative 6, negative 6. And that is another way that we can graph the absolute value function.